Hi, how are you?
Do you have any PowerPoints or anything?
No.
All on the lecture boards?
Just all of this.
Trunks? Trunks is like this, like 60 or Nobody tells us Electron. Yeah.
It's still limited, but at least I don't have to bring paper. Like sometimes I still like to, but I'm getting used to it.
All right, let's get started. So my name is Csaki. I'm from Cornell. And this is actually the 5th time I'm here at TASIS. So thank you very much for the locals for having this amazing, tradition. And everybody should really appreciate it because this is the place where you get to know your future colleagues, your future collaborators, your future friends, and your future enemies. So which is actually all true. So and I like to start always with a little anecdote. When I was here as a student in '95, famous string theorist Nati Seiberg was one of the lecturers. It was at the height of Seiberg duality, and he was asked, how many of these people here does he think will eventually get a faculty position? And he said, 1, maybe 2. Boy, was he wrong. I mean, we have a rule that Seiberg is never wrong when it comes to SUSY gauge theories, but on this one he was really wrong. There was at least 20 people who got faculty positions, so that's the way you should think about it. Another thing, so since I have been here many times, I have many TASI t-shirts at home, so every day I'm wearing a different one just to give you motivation of doing a good one. I think this is a good one. Okay, so it's sort of minimalistic, but it has style, and of course it was designed by Flip, so it must be a good one. All right, very good. So I was asked to lecture on non-supersymmetric beyond the standard model building, and this is a huge topic, so we have a lot of things to cover here. And of course I won't be able to cover every model, and I was trying to focus on sort of the most mainstream aspects of them. So the plan is that today we'll be discussing a little bit what the hierarchy problem is. Yes, and what the possible ways around solving the hierarchy problem are. And then we'll get started with discussing Goldstone bosons, pseudo-Goldstone bosons, and the topic for this morning will be how to write down a nonlinear sigma model, yes, that is giving the effective Lagrangian for Goldstone bosons, how to find what the cutoff is, and look at QCD and a little bit of chiral perturbation theory. And in the afternoon, I will start using this machinery that we are building up this morning to start building the so-called little Higgs, pseudo-Goldstone Higgs type models. And then we'll see how far we go. The next topic after that will be extra dimensions, and mainly warped extra dimensions, though I'm planning to also mention a little bit the large extra dimensional scenarios. And then ADS-CFT, warped extra dimensions, so that will be one big topic, and then how to connect all of that, the warped extra dimensions, to the composite Higgs, little Higgs ideas, and hopefully we'll get a little bit to deconstruction. And if there's still time, which I highly doubt, then the ultimate goal is to get to twin Higgs models eventually. So as you can see, it's a pretty ambitious plan. And so today, this morning, will be the hierarchy problem, and then effective theories. This chalk is really bad. For Goldstone bosons. Yes, so let me see if there is one that is less awkward. And after that, as I said, later today we'll do the little Higgs collective symmetry breaking pseudo Goldstone boson Higgs ideas. All right, so let's get started. So we are going to be talking first about the hierarchy problem. So hopefully everybody has heard about this, and it's related to the properties of the Higgs in the standard model. So the Higgs in the standard model is an elementary scalar, and if you start calculating the quantum corrections to the mass of the Higgs, it's quadratically divergent. So in the Higgs, you have the Higgs potential minus mu squared times h absolute value squared plus lambda times h absolute value to the force. It's the usual standard model, SU2 cross U1 doublet with hypercharge, yes. And you're starting to calculate the quantum corrections to the Higgs potential, yes. So there will be several contributions. Yes. We're looking at the 2-point function, and in particular, you're interested in the corrections to the mass parameter in the Higgs potential. Yes. So there will be several kind of contributions at one loop order. Yes. So there will be fermion loops. In particular, the most important one is the loop from the top quark. Yes, because this is the Higgs. Yes, the Higgs gives a mass to the fermions. The heavier the mass, the bigger the coupling of the fermion to the Higgs. Yes, so the top has a large Yukawa coupling. In fact, it's 1, depending on what normalization you use for the VAV. Yes, so there's a top Yukawa coupling here. So this will be the largest contribution, but there will be similar contributions from gauge boson loops. So you can have here the W and the Z running. Yes, and there will be contributions from the quartic self-interaction of the Higgs itself. Okay, so you start calculating it, and you find that, well, you know, the usual Feynman rules. Yes, there are 2 fermionic propagators here, so you have an integral d for k over whatever 2 pi to the 4 doesn't matter. Yes, and you just have 2 fermionic propagators or 1 bosonic propagator. Yes, so this is going to be something of the order k squared minus m squared. Yes, so this will be quadratically divergent. So if you just do the most trivial thing, which is a cutoff regularization, yes, you will be finding contributions to the mass of the Higgs at one loop, the mass parameter. So let me say delta mu squared. So that's the correction to that parameter. Yes, there's the cutoff here, and then there's 32 pi squared, and you get several contributions. So one is here the top Yukawa coupling. Then you will get contributions from the W and the Z. There is a 9g squared plus 3g prime squared plus 6 lambda. So this lambda is the Higgs quartic self-interaction. Okay, very good. So the question is, what are we supposed to make of this? Yes. So what you find is, of course, that if lambda is much bigger than 1 TeV, yes, and what is much bigger depends on, you know, what kind of model you have in mind. Yes. So if lambda is much bigger than 1 TeV, for example, could be 10 TeV. Yes. That's one option there. This is what you would call the little hierarchy. Or if you take it of the order of the Planck scale, yes, and to the 19 GeV, this is what is called the big hierarchy. Yes, you find that the corrections, the one loop corrections to the mass of the Higgs, are much larger than the actual physical parameter that you know is coming into the potential. Yes, because you know actually what this potential is. Yes, so once you know what the mass of the Higgs is, and you know what the mass of the W and the Z is, these parameters here are completely fixed. Okay, so you minimize it, of course, as usual. I presume Sally did that. You get that V squared is mu squared over lambda. Yes. So V is the usual electroweak symmetry breaking valve that gives the mass of the W and the Z. So that's 246 GeV. And so that's one combination that is fixing the Higgs potential. And then the mass of the Higgs itself, the physical mass, is √2 lambda times V. Yes. So that will tell you, now this is 125 GeV. Yes. So this will tell you that lambda is 1/8, so everything is fixed here. And you see what this parameter mu is, yes, it's something of the order of 100 GeV. Yes, and the corrections, if this cutoff is very large, yes, want to be much larger, many orders of magnitude larger than what the physical value is. So that means that there has to be a large cancellation. All right, so that's the hierarchy problem, yes? So the hierarchy problem, the way we will say it is that the Higgs mass parameter is quadratically sensitive to any new physics. Yes? So the hierarchy. And this is something that is, you should pay attention to the wording. Yes, what I said is that it's quadratically sensitive to any new physics that is showing up at a high scale. So what this the way we are interpreting this lambda is that this is the cutoff scale, yes, at which the standard model ceases to be the right description of nature, yes. And of course, we haven't really seen anything, but the assumption is that at some scale, the standard model will cease to be will cease to be the right description of nature, yes. We have at least two reasons to believe that this must happen at some scale, yes. One is the fact that you have hypercharge, yes, and hypercharge is the U1 hypercharge in the standard model is not an asymptotically free theory. So it will, when at the very, very large scale, it will certainly blow up. Yes. So reasons to believe there is some scale lambda where the standard model breaks down is, well, one is just U1 hypercharge. Yeah, so it's a not asymptotically free theory. It's a U1. It has a lambda pole. It's at a very, very high scale, but if it's that high scale, then that cutoff would be super large. Yes. The other one is at some point you will have to include gravity.
So do you know why it's the plus scale?
I'm sorry? No, it's even higher.
Oh, it's even higher.
Yes. So this is a lambda pole. I forgot what scale it is. I don't know, 10 to the 32 GeV. Some huge scale, yes. But I mean, if somebody tells you this is it, there's nothing absolutely there, yes, then even that is an in-principle problem. Yes. Of course, at a lower scale, you have gravity, so you have M Planck. So at some scale, you would really think, even the purists will have to admit that there has to be, some additional new physics. Of course, we hope there is dark matter. Yes, we don't know if it's really coupled to the standard model or not. But there are many hints that tell you that this is really not the final theory. Okay, so what this lambda is standing for stands in for the scale of new physics. So the kind of arguments that say, well, you know, this is a quadratic divergence, and you know, if I actually do a different regularization, for example, dimensional regularization, there are no power law divergences, I think are pretty pointless, because they're really missing the point of what the meaning of the hierarchy problem is. Yes? Because, you know, if you just say that, well, why not use dim reg? Yeah, so in dimensional regularization, again, you know, there are no power law divergences. There are only log divergences. Power law divergences are all regulated to 0. Yes. So is there truly a hierarchy problem? Again, if you say that it's the standard model, there's absolutely no new physics ever. Yes. Then probably, you know, you shouldn't worry about the hierarchy problem. Yes. I don't believe that it could be just the standard model, you know, and nothing ever. Yes. And then the statement is that whenever there is some new physics, the Higgs is expected to be quadratically sensitive to whatever that new physical mass scale is. So whatever the new physical mass scale is, yes, that is supposed to eventually find its way into the correction to the mass of the Higgs. Okay, so just to give you a concrete example, and again, you know, this is just to, you know, this is a stupid example, but it's supposed to, what it's supposed to show you is that it's not dim rag versus cutoff that you are worried about. Okay, so let's just say there is another scalar. Yes, of course, you know, it's another scalar. It has its own hierarchy. Yes.
If you were able to build a theory that would couple it all to the Higgs, but would fix those three problems, would you not be worried about the hierarchy problem?
Possibly, yes.
So, regarding the lambda model, just before that scale comes as tracking, you know, like how Qcd works at all.
Well, but that's the opposite, yes. So you go to low energies, and you. So what this is telling you is that the theory, the U1 theory breaks down, yes, at a very high energy. So you would think. So the question is. So it is a perfectly good effective theory, yes. The question is, does that theory make sense at very high energy? Yes? So if the claim is that, look, it's just a strongly coupled theory, maybe the lattice people can perfectly make sense of it, yes. Maybe it's not a problem, yes. So again, you know, I mean.
We can't save you.
No, I don't believe that, but you know, I mean, we don't really know what that theory is, yes. So again, you know, so what you should think about the hierarchy problem is that, yes, I mean, this is not an experimental problem, yes. It is a problem of, you know, do you believe the standard model is the final theory or not? Yes. And if it is not, then we think that, you know, it does not seem possible to, you know, get around this without, you know, having new particles. Basically, that's what this whole argument is about. Yes. All right, very good. So I just wanted to show you a concrete example here, yes. And again, you know, it is not because it's a good BSM for anything, yes, but it's just trying to emphasize the fact what the meaning of this cutoff is, that it's not some sort of, you know, the way you should be thinking about it is that this is a physical scale, yes, that this is truly an effective theory, the standard model, with valid below a certain physical scale, and at that scale there will be new particles showing up, and this lambda is supposed to be a stand-in for the masses of those new particles. Yes, so let's say that we have another scalar, yes, and it has some stupid interaction, yes, h squared, s squared, yes, whatever, it doesn't matter. You know, then what you can do is this thing can, you know, can give you additional contributions to the mass of the Higgs. Yes. So you can now close up this S loop, yes, and you will get an additional contribution to the to the mass parameter, yes, lambda s over 16 pi squared. Of course, it will also be quadratically divergent, yes, and then there will be a finite contribution, yes. Well, not quite finite, but log divergent, yes, plus finite. So the thing that I want to emphasize is that even if you believe that, this lambda itself doesn't have a meaning, yes, there will be a finite contribution, yes, that is proportional to the mass of that new particle. Yes? So if this S is a very heavy particle, the heavier you make it, even the finite contributions or log divergent contributions will cause a large correction to the mass of the Higgs. And this is truly the way you're supposed to be thinking about this cutoff scale. Yes, that it's actually standing in for the mass of these new heavy particles that are there. Eventually, hopefully, of course, it's not a stupid model like this, yes, but it's a model where that new particle actually cuts off this quadratic divergence. Yes, that will be the aim of these models. Yes. Well, so if the theory is not perturbative, yes, then of course, that will tell you that there's, the standard, the nice thing about the standard model is that it is perturbative at very high scales, yes. So you're telling me if it's not, then there is already some new physics there, yes. Then there is already, physics beyond the standard model, because, once you go to high energies, the standard model is just perturbative, and that's it. Okay. All right. So that's, if you. That, of course, you can say, well, what if this new physics is not directly coupled to the standard model? Yes. Yes. So then what happens is that it will not come in at one loop, but maybe comes if it's not directly coupled to the Higgs, yes, but it coupled to the standard model fermions, yes. Then, those fermions will couple to the Higgs, and then, that new physics will couple to the fermions, yes, and then you will get a correction at two-loop order, yes. So again, this is just, to argue that eventually you're expecting that any new physics, yes, that is interacting somehow with the standard model will eventually feed into the mass of the Higgs, yes, and will give you this problem. Okay, another way of saying it is that, well, if you look at the standard model, yes, the Higgs mass parameter is the only relevant operator in the theory. Okay. So as you know from renormalization group, yes, relevant operators are the ones that are growing towards the IR. Yes. Okay, and the Wilsonian statement in this case will be that you have to very finely tune your renormalization group trajectory, yes, such that the theory in the infrared actually flows to one where the Higgs mass ends up to be very light. Yeah, so the renormalization group trajectories have to be very finely chosen, yes, meaning that most RG trajectories will miss the point where the Higgs is Higgs is 125 GeV, yes, and there's only one in whatever 10 to the 16, yes, that will actually hit this.
So,
yes.
So when you say light, you mean with respect to the amount of running that you have from the Planck scale?
Yeah, exactly. So you assume that there is some reasonable theory at a high scale, yes. You are choosing, some boundary conditions there, yes, and then you see what will the IR, the low energy effective theory, look like, yes, and most of them will not have a light Higgs. Okay, very good. So another thing that I want to, so one thing I want to emphasize is that this is the only relevant operator in the standard model, yes. So this specific, that's one reason why this is specific to the Higgs. Another thing I want to emphasize is that this hierarchy problem is specific to elementary scalars. Yes, because if you look at mass terms for fermions or for gauge bosons, there's something special happening in the limit when you take the mass of a fermion or a gauge boson to 0. Yes. When you take a fermion, yes, let's say you take the electron, yes, and you take the mass of the electron to 0, well, you know that the electron is a Dirac fermion, yes, which is made up of a left and a right-handed chirality. Yes. And the only thing that is connecting the left and the right-handed chirality, yes, is the mass of the electron. So in this limit, there's a new symmetry. There's a chiral symmetry, which is the independent rotation of the left-handed and the right-handed components of the fermions that is showing up, which will make sure that the corrections of the electron mass, yeah, so the corrections, the quantum corrections of the electron mass, have a very different behavior than the corrections to the Higgs mass. Yes? So the corrections to the electron mass, because you have this chiral symmetry, yes, the chiral symmetry is not allowing you any corrections to the mass of the electron. Yes, so any corrections to the mass of the electron must be proportional to the mass of the electron itself. Yes, so it must be proportional to the mass of the electron, and then well, it could still be log divergent. Okay. Same thing for gauge bosons. Yes, if you take the W and the Z, yes, and push their masses to 0, there is a new symmetry. It's gauge symmetry. Yes. So when you try to calculate the correction of the W and the Z, yes, they must be proportional to the mass of the W and the Z themselves. Sorry? Oh, well, I don't know. So you are not. So I shouldn't write on that board, or? Okay. Well, it's log lambda over mw. Yes.
So, because we do know that the only way to keep a consistent mass of electron boson is via Higgs.
Right.
And this is sensitive to Higgs mass itself, and hence is quadratically sensitive.
Absolutely. Yes.
So I think that the last part is valid only when it's exactly wrong.
Right. So of course, the problem with the hierarchy is not, it is a whole problem of the standard model. Yes, it is propagating eventually through to the mass of the W and the Z. Yes, but it's through the correction to the Higgs. Yes. Yes. No, I mean, if you are telling me that, so one possible way would be to say that, well, the theory does become scale invariant at 1 TeV. That would be a perfect, or 10 TeV, yes, or that would be a perfectly good solution to the hierarchy problem, yes. But it would still tell you that there is new physics at, whatever, 1 TeV or 10 TeV. If you're telling me that there's no new physics at all. Yeah? So the thing that I want to argue here is that there's got to be, if we really believe this, yes, there's got to be some new physics that is getting rid of this. Okay, so if the answer is, well, the theory just becomes conformal, and it's a nice conformal theory above scales where we have tested it, that's fine with me. Yes. What I don't believe is that you say that the theory becomes conformal at 10 to the 16 GeV, yes, and that is going to solve the hierarchy problem, yes. So that's the important distinction. That some people may say that, oh, it's conformal at a very high scale, and because of that there is no hierarchy problem. Yes. So that part I don't think is right. Yes. But yeah, sure, of course, there are many different ways of getting rid of this. Yes, so that's exactly the thing that I want to come to next. Yes, so what is the way out of this? Yes, so way out is that there should be some new physics. Yes, so the cutoff shouldn't be very large. So this lambda better be something of the order of a TV. And by this, I mean where the standard model ceases to be a good theory. So that's where the scale where the new particles should be showing up. Yes, because there was I wrote down over there. Yes, so the correction to the mass of the parameter is basically roughly lambda over 4 pi. Yes, so one loop will gain you maybe a factor of 10 or something like that in the mass scales. Yes, so 100 GeV, the cutoff of the order of a TeV would be a natural theory. Okay. So that would be the new idea, the idea. Yeah. So the cutoff should not be very large. So there should be new particles showing up at that scale. Yes. But it shouldn't just be arbitrary new particles, yes, because arbitrary new particles showing up at that scale, doesn't on its own solve the hierarchy problem. But it should be such that once you take the effect of these new particles into account, yes, at that point, yes, there shouldn't be a quadratic sensitivity to the cutoff left anymore. So whatever this new physics is, that comes in here, should be such that the quadratic sensitivity is eliminated. Okay, so so it's asking for a specific form of new physics. Okay, so what are the possible directions to achieve this? Okay, well, one is called supersymmetry. But the basic idea is to go back and see, what are other ways, how do other particles get around the hierarchy problem? Yes. So fermions don't have a hierarchy problem. Yes. Scalars do. So what supersymmetry does is it finds a way of relating a scalar to a fermion. Yes. So there's sort of, these two layers. Yes. So there's a chiral symmetry for the fermions, and there's supersymmetry that is relating scalars to fermions. So the two together is sufficient, yes, to eliminate the quadratic divergence, the quadratic sensitivity of the Higgs mass to high scales. Okay, so again, so the idea here is there is a new type of symmetry that is relating fermions and scalars, and in general bosons and fermions. And then using the chiral symmetry, yes, is going to be sufficient together with supersymmetry to protect the mass of the Higgs. Okay, so that's the topic of Howie Haber's lectures. Yes.
Yeah. So my question is about the first line, the argument that we should have to see some physics, but from the recent work on using the cosmological ideas.
Right. So that's a different direction. Yes.
So the border type. Right. What would be the caveat that we have to put in this thing such that this argument is still valid?
Well, again, so this is assuming that. So you're talking about the relaxion, and yeah. So there's some other direction there. So I was hoping to talk about this at the end, but I'm not sure I will. So that is sort of an alternative to this. Yes. So what this is saying is that there's something special happening cosmologically, yes, when that there's nothing special in particle physics, yes, that there is a hierarchy problem, yes. So that's what the relaxion idea is, that there is a hierarchy problem, meaning that the Higgs mass is truly sensitive to the cutoff, and you're allowing very large. But what happens is that somehow cosmologically you're actually scanning over this this very large Higgs parameter, yes, and that something very special is happening when the Higgs mass parameter is actually becoming close to zero or just flips from positive to negative.
Right. So,
would you say that there we are replacing RT flow with Puff with a very different notion of naturalism?
the question is more about when do we really expect most like around the TeV scale. For example, another idea related to this thing is, and then there we expect the new physics to realize like a new neutrino or something like that. Or in the relaxia, we don't expect any new physics possible.
Right. So
yeah, there is a version in expected physics, but there is.
Well, in principle, yes. I mean, I wouldn't go into any details of a particular relaxian model because they are not very pretty, or, you know. But in principle, you can imagine that there could be a version of this, yes, where, you know, there's no new physics that is available, you know, to. So that is a different direction, yes. So I'll try, but I'm not sure I will get to that. But okay, yeah. So this is sort of, you know, the traditional way of trying to get around it. This is the traditional particle physics solution of solving the hierarchy problem. Yes, and yeah. So there are other ways. Yes, there's the multiverse idea. Yes, that you know, well, you know.
Sorry.
Even inside symmetry, I think there are ideas where somewhere in the UV there's some other symmetry that makes you mostly overestimate, right? Which could possibly happen.
Sorry. So you mean, so if you have supersymmetry, then you solve the hierarchy problem. Yeah?
But still, if SUSY at a higher scale than a TV, will have tuning problems.
Right.
There's some other route which makes you overestimate
I'm not sure about that. That's there are people who claim that, yes. There are people who claim they can predict the Higgs mass to, you know, whatever, 6 digits, and there's, well, they say after the experiment, they say they did it before the experiment. Anyways. All right. So that's important. So we are going to be focusing on the traditional particle physics solutions. Yes. So this relaxion idea is a different direction. Yes. So it is this idea. You know, if I have time, then I will say a few words about it. Is that there is a hierarchy problem, but it doesn't matter. Yes, because there's something else that is going to pick for you. You know, the point that we are seeing in the standard model, and that's, you know, something happening. You know, there's a phase transition happening, or, you know, something around when the Higgs mass is flipping sign. Okay, so that's a different idea. All right. So SUSY is one of the traditional particle physics solutions. Yes, and I will not be talking about it. That's Howie Haber's lectures. So I will be mainly talking about the other interesting direction, yes, which is using Goldstone's theorem. Is this visible to everybody? No. Here? Good. So Goldstone's theorem, of course, hopefully everybody knows that. It says, you know, if you have a global symmetry that is spontaneously broken, yes, then you do have a massless scalar. Yes. So there is a way to get a massless scalar from a symmetry argument, yes, and that's Goldstone's theorem. So a spontaneously broken global symmetry gives rise to massless scalars. Yes. So the question is, can you use this symmetry, yes, to protect your Higgs mass from quadratic sensitivity? Yes. And so this will be the crucial idea that I will be focusing on in this series of lectures. Yes. And there are several versions that will be all making advantage of this Goldstone's ideas. So one is that the Higgs is composite. Yes. And there is no true elementary scalar. Yes. Let's say it's a theory of fermions. It's similar to QCD. Yes, there are no scalars, no elementary scalars in QCD yet. We see some, we see some light scalars there. Yes. So maybe the Higgs is something like that. The Higgs is composite. Yes. So there's no true elementary scalar, just composite scalars. Yes. So it turns out we will still need Goldstone's theorem for this to solve at least the little hierarchy problem. Yes. Then there will be another implementation. All of this will be eventually boiling down to the same thing: the warped extra dimensions. And you will see, using the ADS-CFT duality, yes, that these ideas, at least from the point of view of their solution of the hierarchy problem, are actually the same thing. Yes. So they are just different bases of writing down roughly the same statements. Okay. Then there is another direction that is called gauge-Higgs unification. So here the idea is that, well, supersymmetry relates a scalar to a fermion via supersymmetry and then uses the chiral symmetry of the fermions to solve the hierarchy problem. Well, maybe if you could somehow, make the Higgs secretly be a gauge field, yes, then you could use gauge invariance to solve the hierarchy problem. Yes. Of course, in order for this to happen, you also need extra dimensions. Yeah, so there the idea is that maybe the fifth component of the gauge field, yes, so you have the usual 4 components of the gauge field, which are whatever we observe in 4 dimensions as a gauge field. We will talk about this in detail. Yes, but then there are the higher dimensional gauge field has these additional components, which from a 4-dimensional point of view will show up as a scalar. Yes, but there is a secret higher dimensional gauge symmetry that is relating those scalars to the gauge bosons. Yes, so that's another possibility. Yes, and it turns out that eventually, what now people consider the pseudo Goldstone boson composite, minimal composite Higgs, actually takes advantage of all of these. Okay, it is actually a warped extra dimensional theory where the A5 is the Higgs, yes, which can be interpreted as a composite Higgs in a 4-dimensional theory.
But you're saying you can only have these and not have Higgs as composite. Like you only have 3, but avoiding first one.
No, so it turns out that this from the ADS-CFT duality will still be interpreted as a composite Higgs. Yes.
And it's correct to say that the fact that the Higgs for the PhD solves the little hierarchy
right.
problem. So what solves the large hierarchy problem is actually computation.
That's a precise, yes. So this will solve so this will allow you to make the cutoff scale to be 10 TeV, yes. And then at that 10 TeV, that's where your Higgs is going to dissolve, yes, and become those more elementary degrees of freedom, yes, that then will have no big hierarchy problem. Yes. Very good. There have been more radical ideas. Which at some point didn't seem to be so radical. Yes. So one was called Technicolor. And we'll briefly mention this. Yes. So here there was actually no Higgs at all. You still have a strongly interacting theory like in this composite Higgs scenario. Yes. But what the strong dynamics does is it breaks the electroweak, when it breaks its chiral symmetries, like QCD breaks its chiral symmetries. Yes, what it does is it directly breaks the electroweak symmetry without, the need of a Higgs. Yes, so this was actually a favorite for people, back in the 80s, Yes, so this, back in the 80s, if you talked about supersymmetry, you were crazy, and everybody believed there's Technicolor, yes, because it is by far the simplest idea, yes, and needs, the least, the least amount of imagination beyond what we already know, yes, because it just needs another version of QCD. Yes, well, of course, the problem is it says, well, there are several problems with it. One is, the biggest one is that it says there is no Higgs, yes, and we know there is a Higgs. Yes. And, of course, it also had problems with electroweak precision. It also had problem with flavor, so eventually it's not so nice. There were also extra-dimensional versions. Those were called Higgsless theories. I really loved them because I made them up, but sadly they are excluded, so I'm not going to talk about that. And then there is another radical idea, which is called large extra dimensions. So I will briefly mention these. So what this is saying is that, well, actually, the hierarchy problem is just a mirage. Yes, and the fundamental scale of physics, the true fundamental scale of physics, including gravity and everything else, is actually the TV scale. So there is nothing to explain, yes, because, I mean, what you usually think of is, well, there's some new physics coming in at some more fundamental or new scale, yes, but there is no such a thing. Everything happens at the TV scale, including gravity, yes, and there's nothing to explain. Of course, then you have to explain how come gravity, its fundamental scale is a TeV, yes, but it appears that the Planck scale is 16 orders of magnitude bigger. Yes? So that's the job you have to do here. So I will hopefully spend half an hour on that probably tomorrow. All right, very good. So I will have some literature. I have written many reviews on on these related subjects. So I will put that in the notes. I'm not going to list it because I'm not going to waste my time on that. All right. So as I said, these lectures will be mainly focusing on these ideas, yes, and as you can see, one of the crucial ingredients here is, the Goldstone theorem, and so what I would like to do in the remaining 1 hour today, yes, in the morning, is to write down, how to formulate the effective Lagrangian for Goldstone bosons. What do we use for eraser here? Just an eraser, yes. Okay, so Goldstone bosons. Not good, not good. All right, so everybody knows Goldstone's theorem, yes. You have a spontaneously broken continuous symmetry, and you get a massless scalar. Yes, it has to be a continuous global symmetry. So the question that I would like to ask is how to write the effective theory for such a theory. Yes. So what is the physical intuition for this Goldstone's theorem? Yes. And the physical intuition is that you have a potential, yes, that has a continuous symmetry which is spontaneously broken. Yes. So what happens in that case is that if the symmetry is spontaneously broken, yes, you must have a valley, yes, at the bottom of the potential, yes, which doesn't cost you any energy to move around. Yes. So the minimum of the potential It's not unique. Yes. And again, this is a consequence of the symmetry. Yes, because you take one minimum and you can, just do the rotation by the symmetry. Yes, and you get another minimum. Yes, and the spontaneous breaking, truly, that's the definition, that you take one minimum and you rotate it and it goes into another minimum. Yes. So it's completely, from this point of view, this is completely obvious and trivial and intuitive. Yes, that there's got to be a valley. Yes, around on the, that is forming the minimum of the potential, and these are all degenerate minima. Yes, and it doesn't cost you any energy to move around. Yes, so the Goldstone boson is literally the motion along the valley of this potential. And again, so it's very intuitive, and these directions are connecting different VAVs via the symmetry transformation. Yes. So what I want is then how to write down this effective theory for just the degrees of freedom that are corresponding to motion here. Yes, versus other degrees of freedom. Yes, that would be corresponding to massive excitations. Yes, which would be motions in orthogonal directions. Okay. So, and the important thing is that I won't care whether this is coming from a fundamental scalar theory or from a strong interaction, yes, that had a global symmetry. Yes, so this formalism doesn't care if the UV, whatever had this symmetry, yes, that theory was a theory of fundamental scalars, for example, the standard model, yes, or it is a strongly interacting theory like QCD that doesn't have fundamental scalars but has spontaneously broken global symmetries. Yes, the same thing has to apply in both cases. Yes, care what UV is. All it cares is that there is a global symmetry that's spontaneously broken, and we are trying to write down a low energy effective theory of those degrees of freedom, leaving out, yes, integrating out the massive degrees of freedom. Yes, so those could be these radial modes. For example, for the standard model, this would be a theory of just the Goldstone bosons, yes, without even adding the Higgs. Yes, the Higgs would be this radial excitation, and the Goldstone bosons would be these things that are eaten by the W and the Z. Yes, or it could be the effective theory for pions in QCD. Yes. Now, of course, this will be an effective theory, so this will be called the Chiral Lagrangian, and this is an effective theory. Yes. And that effective theory will have a cutoff. So we will have to eventually find what that cutoff of that effective theory is. Yes. So we will try to make an argument for that. Okay. So first I want to build this Chiral Lagrangian and then find what the cutoff is. So I hope I will still be able to do that. Okay, so first of all, what is the Chiral Lagrangian? Yes, so we have a global symmetry G that is broken to H, yes, via some mechanism, yes, and there is a VAV V0, yes, which is giving rise to the breaking, and it doesn't really matter what the origin of that VAV is, if it's a scalar or a strong interaction. Yes, so let me call this U0 here. Okay, so what you can do is then you can take this VAV, yes, and act with this VAV, act on this VAV with one of these global transformations. Yes, so what you're supposed to do is you're supposed to get another minimum of the theory. Yes, so you're going to take e to the I epsilon a t a, yes, and acting on this VAV, yes, and these will be the generators that are broken by the symmetry. Yes. So this is supposed to give you some, I'm sorry? Broken by the valve. Yes, I'm already thinking about the next sentence. So these are the generators that are broken by the valve. Yes, the symmetry generators. And of course, the ones that are not broken, you can apply it here, but you will have no effect. Yes, because this is a valve. Yes, so there are two kinds of generators: some that are broken, some that are not broken. If you act on with the ones that are unbroken, yes, nothing happens. Yes, because they will annihilate that valve. Yes, because it's not broken. Yes, but the ones that are broken, yes, those are going to rotate this field. Yes. So basically, this transformation parameter here, yes, so that is telling you truly the motion, yes, around the minimum of this potential. Yes. So what this Chiral Lagrangian formula does is it says it's truly these parameters, these transformation parameters, yes, that you are supposed to be identifying with the Goldstone bosons of the theory. And so these should be identified with the Goldstones. Okay. So, oops. So I will take this epsilon, yes, and I will promote this to a field, yes, and I will call these the Goldstone boson fields divided by some decay constant. Yes, so this is now a field, should be dimensionful. Over here, this was a dimensionless transformation parameter. So if I promote it to a field, I should divide it by some constant. This is what is usually called the decay constant of the theory. And these pi's are the Goldstone bosons. Okay. So this is what you call the nonlinear realization of the symmetry. And you will see in a moment why it's a nonlinear realization. And this field here is what is called the nonlinear sigma model field. Okay, so this pi over f, yes, is basically just an angle of transformation. So let's try to see the simplest example, the one where this is not yet fantasy theory, it's QCD, and the Chiral Lagrangian for QCD. So what you have, of course, it's nice because we know now what the actual Lagrangian for QCD is. It's an SU3 gauge theory with a bunch of quarks. But I want to emphasize that this approach about the Chiral Lagrangian predates, the knowledge of what the true QCD Lagrangian was. Yes, because again, it's so simple and it's just based on the global symmetry aspects of the theory, and that was something that became apparent before the true dynamical nature of QCD has been found. Okay, so but of course we know it, so why don't we take advantage of it? Yes, so you just have the gluon fields, yes, mu a squared, and then you have a bunch of quarks, sum over I q bar I d slash minus q I. Okay. So this is the QCD Lagrangian. Yes. And the nice thing about this QCD Lagrangian is that in the limit, when the quark masses go to 0, yes, you will have a large global symmetry for this theory. So for example, for 3 generation, for 3 flavors, yes, so 3 quark flavors, not 3 generations. So up, down, and strange, 3 flavors. Okay. 3 quark flavors. You will have an SU3 left cross SU3 right, chiral symmetry, chiral global symmetry, yes, under which the left-handed and the right-handed components of the quarks are transforming into each other. Okay, so what you have is these quarks. Yes, these are Dirac fermions, and you have a left-handed and the right-handed component for them. Yes, and in the limit, when the quark masses go to 0, you can just go ahead and transform them into each other. So they are all fundamentals of SU3, yes, of QCD, yes, and then you can think of these as the fundamentals of SU3 left and fundamentals of SU3 right. Okay. Very good. So that's all very nice. So you have in the limit, when m goes to 0, yes, your right-handed quarks transform into each other via a 3x3 right-hand, this transformation matrix, yes, and your left-handed guys transform into each other via a 3x3 matrix. Yes. So these are the transformations for the chiral symmetry transformations. Yes, very good. So the important thing is that this is a global symmetry. SU3 left cross SU3 right is a global symmetry. So it's not the gauge symmetry. So this is the kind of symmetry that Gell-Mann was thinking about, yes, back in the 60s. So it's a global symmetry. This is different from the SU3 color symmetry, yes. So you take the SU3 gauge symmetry, the SU3 color symmetry, and in the limit when the quark masses are very small or negligible, yes, there's an additional global symmetry where you just rotate these 3 flavors of the quarks into each other. So this is a global symmetry. Yes. So the global symmetry should be realized on the spectrum of the theory. Yes, this is a physical observable. This is physically observable. Yes, unlike gauge symmetry, yes, because gauge symmetry is a weird symmetry, yes. All the physical observables should be gauge invariant quantities, yes. So that's something that's harder to. But this global symmetry should be physically observable, whatever happens to the gauge symmetry. To SU3 color. Yes. So of course we know that what happens to SU3 color is that it becomes strongly interacting. Yes, QCD is becoming confining. Yes, but this global symmetry should still be there. Yes, because this is an approximate global symmetry of the whole gauge dynamics. Yes, and it doesn't matter whether the gauge dynamics become strong or not. Yes, this should be there. Yes. So, but then what you say is that, okay, so now let me look at the spectrum of bound states and try to classify them according to this SU3 left cross SU3 right global symmetry. And you find that's not possible. Okay. The spectrum does not have SU3 left cross SU3 right global symmetry. It does have some global symmetry, but it's smaller than this. Okay. It turns out that you only have one SU3 left that is visible on the spectrum, and that's the SU3, yes, that Gell-Mann found back in 1960 few, yes, as the eightfold wave, where, according to which you can actually classify all the observed hadrons, yes. But this bigger one is not there. Okay. So how should we interpret that? Yes. Well, the only way to consistently interpret it is to say that, well, QCD became strongly interacting, yes. It did form bound states, but it did also something brutal to this global symmetry. It broke the global symmetry spontaneously. So the QCD vacuum, yes, breaks the global symmetry. Okay, so there's a quark condensate in the QCD vacuum, yes, and the quark condensate should be such, yes. Well, how do we know? Well, there, in the 60s, the way we knew it is because we looked at the spectrum of the bound states and we saw this is a symmetry, and the bigger one is not a symmetry. I guess by now, from QCD, from lattice, etc., we know it better, but we knew this already beforehand. So that means that there is a non-trivial quark condensate in the QCD vacuum. Yes, so this must be proportional to. So this is, let me write it out. Q bar left I, Q right J plus Hermitian conjugate. Okay, and this should be proportional to delta ij. Yeah, so this is a flavor quantum number of the left-handed guy. Yes, and this is a flavor quantum number of the right-handed guy. Yes, and the condensate has to be such that when I do a combined SU3 left and SU3 right transformation, it's left invariant, so it's proportional to delta ij. Yes, and then there's some scale here that is telling you what the dynamics of the theory is. Okay, so that tells you that, well, so there is an SU3 left cross SU3 right spontaneously broken. You expect there to be Goldstone bosons. Yeah, so there should be 8 Goldstone bosons. Now, of course, there are no true massless scalars in the standard model, but there are 8 particles that are lighter than the others. Yes, so those are the pion, the kaons, K bar, K plus minus, and eta. Okay, very good. So these would be true Goldstones in the limit when there was no explicit breaking. Okay, so in the limit, you would expect that these hadrons are truly massless. Yes. Now, of course, this symmetry of the Qcd Lagrangian was not actually a true symmetry. Yes, because I said it's a symmetry in the limit when the quark masses go to 0. Yes. In reality, the quark masses are not actually 0. Yes, they are small compared to the Qcd scale. Yes. But not exactly vanishing. Yes? So there will be some corrections to their masses, and that's something we'll be calculating in a moment. And there are other explicit breaking terms, which is coming from the fact that some of this SU3 cross SU3 symmetry is actually a gauge symmetry. Yes? So gauging a diagonal subgroup is also an explicit breaking. Okay. So first question is, where is the electroweak symmetry? From the point of view of QCD, yes, it's a yes. So of course, the quark mass itself is coming from the Higgs, yes. But from the point of view of this, global symmetry, yes, this you can treat it as an explicit breaking, yes. Okay, very good. So first of all, where is the electroweak symmetry? Yes. Well, so the electroweak symmetry can be embedded inside this SU3 left. Yes, so the SU2 left cross U1 hypercharge, yes, can be embedded into SU3 left cross SU3 right cross U1 baryon number. I didn't mention there are two additional U1s. There's baryon number, and then there's the axial symmetry. The axial symmetry is anomalous, so we won't be talking about this. Okay, so you can embed the SU2 left inside the SU3 left. Yes, so you have your U, D, and strange. Yes, so you have your left-handed multiplets, and then this here is going to be the SU2 left. Yes. Now, of course, this is strange a little bit. The strange is strange because the charm is left out of this structure. Yes. So basically, what you have is you have a very large charm there, charm mass there. Yes. So that's a big explicit breaking. Anyways, so the important thing is that I would like to write down the effective Lagrangian for these Goldstone bosons. Yes. So the way I'm thinking about it is that there is this VAV. Yes. So this one transforms as a fundamental of SU3 left. This one transforms as a fundamental of SU3 right. Yes. So the way I should think about it is when I'm trying to write down this VAV here is that this is like a bifundamental of SU3 left cross SU3 right getting a vacuum expectation value. So this is like a U bifundamental getting a VAV. Okay, so the way I should think about this is that I have my U0 and I have this matrix. So this is a bifundamental. So from one direction it transforms with SU3 left. From the other direction it transforms with SU3 right. And it's getting a vacuum expectation value. And then all I have to do is go ahead and act with the broken generators on this VAV. And then I will be getting my nonlinear sigma model field, for which then I will start writing down a Lagrangian. Okay. So I take this, and so this U0 transforms with U left, U0, U right, dagger. Okay, whether it's dagger or not, that's a matter of convention. Yes, but whether I put a dagger here or not will tell you whether it's the vector-like or the whether it's the combination where I take U left equal to U right, that is left unbroken, or the other version. Yes, because I want U left equals U right left unbroken. Yes, I'm going to take it to be this combination. Okay, very good. And so what you are interested in is the action of this on the VAV based on the broken generators. Yes, so the unbroken generators are the ones where U left equals U right. Yes, because this is a unit matrix here, and this and that is U dagger. Yes, when the two act on each other, this is going to be invariant. So the broken direction is when U left equals U right dagger. Yes, so there will be 8 broken directions, and U left equals U right dagger. Yes, so how should I write this? Well, I write then that U left equals e to the I pi a ta over f. Yes, and then this equals U right dagger. Okay, so the whole parametrization of this nonlinear sigma model field will be that U of x is e to the I pi a ta over f times the unit matrix, yes, times e to the I pi a ta over f. Yes, both of them are the same, so this is clearly the combination where the pions don't drop out. Yes, and you will get yes. Yes, sorry. Sorry. So the whole field, yes, this U of x is, you can just write it as e to the I 2 times pi a ta over F. Yes, and then you don't need to write the unit matrix anymore. Yes, so this is what you call the nonlinear realization of the Goldstone bosons. So how do they transform? How does U transform? Well, under the unbroken symmetries, yes, well, we know that this is a bifundamental, so under the unbroken symmetries, yes, it just transforms as it should. UV e to the I pi a T a over F UV dagger. Yes, so that's the combination when left is taken equal to right. Yes. Or if you want to linear order, yes, so you can linearize this field 1 plus I times pi a T a over F plus higher order terms. Yes, you will just say that pi a T a goes to UV pi a T a UV dagger. Yes. So just like you expect a normal octet of these unbroken SU3 vector symmetries to transform. Yes, so there's no surprise here. Okay, how about the broken generators? Okay, so here this U of x will go to U axial, yes, times Ux times U axial. Yes, so no dagger here. Yes, and this is supposed to be written as the transformed pion field. 2 pi a transformed T a over F. Yes, so this is the way the field transforms. Yes, so this is the transformed field. So I just parameterize it again as the transformed pion field. Yes, and there's no dagger here. Yes, because there is no because this is the broken direction. Yes, this is the direction where where the generators don't drop. Where they don't commute. Okay, so I can go ahead and write this as, let's say, just a normal transformation e to the I C a T a. So this is now the transformation parameter. Okay, and then I can go ahead and try to write this order by order in the fields. Yes, so let me linearize this. So there will be here a 1, and then 1 plus 2i pi a prime T a over F plus higher order terms. So that's the linearization of the left. Yes, and of the right, well, I have to go ahead and write out. So there will be 1 plus I times C a T a. Yes, here I write out 1 plus 2i pi a T a over F plus order pi squared terms. Yes, and then I have to write again. Sorry, this 1 plus I times C a T a over F. Okay. So you multiply through. Yes, and the important thing is, yes, that because this has the same sign, well, the ones, of course, match up, but then the leading term, the way you are going to get the leading term is that pi a prime T a equals pi a T a plus F times C a T a plus order pi squared terms. Yes. So this is a key equation. Yes, it's telling you that to leading order, as under the broken symmetries, the pion is going to shift. Yes, so you probably heard so many times the pion has a shift symmetry. It has a shift symmetry. Where does it come from? It's very simple. Yes, it's you just work out how the broken generators act. Yes, and there the term without the pions is not dropping out. Yes, by construction, yes, because from it has the same sign here, yes. So it will actually shift the pion, and it will give you the shift symmetry. Okay, so that is another proof of Goldstone's theorem. Yes. This is another proof of Goldstone's theorem, yes, because it's telling you that, well, whatever Lagrangian you write down, in order for you to still obey the symmetry that is spontaneously broken, but it's still there, yes, it's just spontaneously broken, yes, you cannot possibly write a mass term, yes, because the mass term is not shift symmetric. In fact, you cannot write any non-derivative term, yes, every term has to have a derivative before explicit breaking. Okay, so I'm going to stop here. So the thing that I couldn't finish this morning that I wanted is then, write down the Lagrangian and the explicit breaking terms, and then do the NDA. Okay, so we're going to finish up this part and then start applying it to collective breaking and pseudo Goldstone boson Higgses in the afternoon. So I'm going to stop here. All right, thank you. Questions? Yes.
So there you argue that because we do not see the full global symmetry in the higher spectrum, there's going to be some sort of symmetric breaking.
Yes.
So you assume that it's going to be spontaneous breaking.
Right. Well,